We'll start the morning off with Seng He from, ATH, Royal Institute of Technology in Sweden, Metamaterials and their energy-related applications.
Okay, good morning, everyone. It's my great pleasure to give a lecture in this great workshop. We have been doing workshop together with Ivan earlier in China. This is more related to energy application. So my first lecture is Metamaterials and some of the brief introduction to the application in energy-related areas. The work is done together with my PhD student and postdoc young faculty. A few names listed here. And come together, not just the KTH, but also COER in China, and we also have joined Science Sweden Research Center of Photonics, Joseph. So the topic is mainly on the energy-related. I want to see whether what kind of application metamaterial can play important role for the energy application. So the main thing is like the new energy, sustainable energy, like the solar cell, and another one how to save the energy when we utilize electricity, like LED lighting, solid-state lighting, and greatly save the energy. So these two areas we will see what a metamaterial can play role in these kind of application. So this is a very general introduction of electromagnetic metamaterials, and conventional material is in this coordination system here, epsilon larger than 1 and mu larger than 1 or equal to 1, typical conventional traditional materials, and we mainly working in this section. And the metamaterial mainly is other than this area, conventional material, whether we can make an electrical permittivity or magnetic permeability with some other value. For example, could be earlier, it started with double negative. For example, both electrical permittivity and magnetic permeability are both negative. That was called a negative index material, double negative. And also you can have the single negative for epsilon or single negative for mu. And recently, also very interesting, is look at the zero index. It's on the axis. Like epsilon on this axis, epsilon equals to 0, and on this axis, mu equals to 0. And there's many very interesting property, kind of abnormal properties with zero index material, and I can show a few examples for energy-related application. So these are the kind of electromagnetic material, and in many cases we have to artificially design these materials and fabricate them. And why it's so great about it? Not just because the property is different from conventional material, and there's many more design parameter choices you can make. For example, if we rely on natural material, and these are material formed by the molecules, atoms, and the atoms we know from the table it's limited. It's over 100. That's the total number of the atoms, different type of atoms you can utilize, and that's the limit. But for the metamaterial, we rely on artificial kind of constituent unit. It's kind of artificial atom, sometimes we call. And this kind of artificial atom, they could be many different types. So the total number of types are not limited. You can make a many different design as you wish. So the property was completely different. You can make the epsilon very large or mu very large, or you can make it very small, even to 0, or even give a very negative value. All these things you can manipulate, control by artificial design. These kind of artificial atom structure. And these atom structure are based on like a spur ring resonator or the kind of special unit. And you can put it down the periodical way or even sometimes randomly put them together. So this, and I just revealed two basic properties which have attracted a lot of attention during the past decade. And then move on the latest one like a zero index or some other thing for the energy related application. But first two properties which are very popular, well known in the community for the metamaterial. One is beta deflection limit. So this is a conventional case. We are living in a world with always positive reflection index traditionally. And if you have a lens, a slab lens, you put a source, it will diverge. And if you want to make a focus of the light, then you put a convex lens, it will convert and focus. However, there's this spot, if you put in an infinitely small point, so no matter how small the point, it will always give you finite spot size at the other side of the lens. So, and this is typically like half wavelength spot size. No matter how large, how perfect your lens is, always have finite spot size. So the resolution is always limited. So that is what we call the traditional deflection limit. And about 4 decades ago, Veslago predicted this metamaterial, if both electroconductivity less than 0 and magnetic probability also less than 0, from energy conservation law, the reflection index N typically take the square root of epsilon mu, must take the minus sign instead of positive sign, a square root. And then it will become the negative. And then when it's negative, then it's putting a point source here, it will be as for slab lens of metamaterial, it will bend in a negative direction, so called a negative reflection, and then give you focusing internally, and then go out focusing again. So this gives you a slab lens for focusing. And with this kind of structure, you can actually see the diffraction limit. And there's the property of this metamaterial double negative is that in this double negative material, the pointing vector is going, if you have the incident field here and the reflected field just as usual, go this way. However, you look at the transmission field into this double negative material, the K vector, the wave vector, actually is in the opposite direction of the pointing vector, where the energy propagates. So K vector is always in the opposite direction of the pointing vector, the energy propagation direction. So that's what we call the left-handed material, because if you look at the E field, H field, and K vector, wave vector, typically form the right-handed loop. So EH and goes like for K according to the right-hand rule. But in this material, it follows the left-handed loop. So EHK, so that's why we call the left hand. And because they actually look like backward wave, like even energy propagate forward, but the wave seem propagate in the backward wave. So we also call the backward wave material, sometimes called this material backward wave material with the backward wave. And that can also play important role later when we discuss a slow line for like a absorber, a broadband absorber. We utilize this kind of backward wave phenomenon to slow down the light. And with this kind of property, and this is different. This is conventional material, and you see follow the Snell's law, and the pointing vector and K vector are always in the same direction. And from the conservation of tangential K vector, and you see it will, this field, this way will go in this direction with positive angle. But here, because K is in this opposite direction of S vector, so tangential K must be conservative, so has to be in this direction with negative angle. So that's why we have the negative reflection comes in. So and then we look at the deflection limit. The deflection limit, mathematically, you can understand in this way. You take the Fourier transform of this point source along the x direction, that's x direction, and then you look at the Fourier component. The low frequency component, they can propagate, always propagate to the other side and restore. So this is no problem called the propagating wave. However, for high frequency components, in the K space, for this higher than the K0, K0 is K vector wave number in free space, and this one becomes exponential decay. So it will exponential decay when it reached to the focusing point. So when you try to collect the light at this point, all the high frequency evanescent component, they are gone. So you can never recover the high frequency component on the other side of the lens, no matter how small your point, incident point source is. So this is the diffraction limit. So you only have the low frequency component. And you get back to the real space, you always have the spot size larger than half wavelength, roughly speaking. But for the metamaterial, it's different. This evanescent component, they can actually, through this material, metamaterial, they can be amplified and increase. This is exponential decay, and here in this material, they actually exponential increasing and reach this border, and then in the vacuum, exponential decay again. And the net result, they could be cancel each other, still remain the high frequency component. And in the ideal case, they will be restored. So then you can be the deflection limit, make the spot size very small, much smaller than wavelength, and that is called a perfect lens or super lens application of metamaterial. So that's how metamaterial became very popular in the old days, 10 years ago, mainly because it's a super lens, perfect lens phenomenon. And people experimentally verify this negative index property, negative reflection, by putting array of a split ring resonator and this at the microwave. It's much easier to verify experimentally. And split ring resonator, it's instead of close the loop of the metal line, you broken this part. So each loop is broken. It's not complete. And if you make it complete, then you cannot have this negative probability. And this is, so I leave one question here. Why is split ring resonator, like this kind of broken ring, you can have the negative mu? So what is the physical reason for this kind of thing? Any students volunteer? Think about it, and later I can come back. What is the physical reason why you need like this kind of split ring, broken ring, to get this mu negative for this case? Another application later after perfect lamp becomes very hot subject is called cloaking, make the object invisible. So mathematically, you can understand it this way. Max equation in different coordinate still vary. You can do the transformation in different coordinate, taking linear transform from this xy coordinate to another coordinate. And in this one is a vacuum space. So the max equation is it can be isotropic, but in this case, could be anisotropic F transformation. And these parameters, epsilon, mu, they are related by this kind of tensor with this J matrix. They are related. So depending what kind of coordination transform, you can get in another permittivity and probability cancel. If we start with a vacuum and then through transformation, you will end up with some other anisotropic material and still satisfying Max equation. However, the material parameter will be changed. So that's the whole thing about the transformation of it. Now we can think about start with the vacuum, a single point, and I do the transformation, make this one point to a hole with the radius r equal to a, and this radius r equal to b will keep the same, outside will be the same vacuum. And then this point will open up, in this just in a mathematical way. However, through this coordinate transform, we can think about just taking this very simple transformation. R equal to b minus a over b, r prime, and plus a. And then this single point, r prime equal to 0, become r equal to a, make a hole. One single point in vacuum become a hole. And this region with the diameters radius less than b become this region. And outside, they will be just keep the same vacuum. And this material transformation from vacuum become this kind of material. And this material, you look at the r equal to a, actually equal to nearly 0. So this will become like a 0 permittivity, a permittivity, 0 index. And then you look at this one, and you put in anything inside this hole, and equivalent from scattering point is exactly same as scattering from a vacuum, which will give you no scattering at all. It's just like propagating goes through. So, and then you can expect that all the field here must be identical to the field here, so the field will be identical to the incident field. There's no scattering at all. So that's why you put anything here, the light will just go through without any distortion at the other side. So that's kind of invisible. So mathematically, you can understand that this way, it's anything you hide here, because it doesn't matter, come back to original space, it's just vacuum. The vacuum, a single point in the vacuum, will never give you any scattering. So this is, but physically you can also understand it, because here the material parameter becomes 0 index. When you have 0 index, the light actually cannot go into this region. So that's why the light comes in, they will never touch inside, so it doesn't matter what's inside, it will not affect the field outside. So you can hide object inside. So the field, and they will go here, gradually move back and restore the face as if nothing there inside. So this is an invisible code. So this is different from conventional invisibility. Conventional invisibility for the radar system is something like this, the radar reflection. People want the reflection to minimize, either like stairs technology, make a special shape and also make a absorbing material. And so the backscattering can be minimized, and even for a bigger, huge airplane, you can make the backscattering so small, just like smaller like a ping pong ball, very small. So then under radar system, invisible, but that is only for the radar system for the backscattering. But nowadays, actually, you don't need that. You can put in the radar system from the incident wave from one place, but the detector could be another point. Not necessarily always a backward in the backscattering measurement. So then you can always measure this object is not invisible. Actually, it's visible when it's maybe invisible like a stairs technology, only make it that invisible for the backscattering. But if you move along to detect it at the side, you will see the object. So this is another really invisible scenario. But for this case, the electromagnetic cloaking with metamaterial, with this kind of special material, and you also see the material actually spatially dependent. It's not homogeneous. This medium is gradually changing with our radius. Different positions have different property material. So all these material you have to fabricate in an artificial way to fulfill the condition. And then with this one, you can make object really invisible. And the convention backscattering is something like this. You can completely absorb the light. You're shining a young gold here, the light is shining this one, and usually you see it, but you make it an absorbing material, coated for radar system invisible. There's no light, no electromagnetic reflected. However, you see the dark shadow, so it's still visible. At the transmission side, you see something going on. From other side, it's a dark shadow, different from the when without this object, you see the tree in the background, but this region you don't see the background at all. There's a shadow there. So the invisible cloaking is made of this transparent, completely transparent, not just absorbing light, made leaving a shadow. So that's the difference of the ideas. And at the optical frequency, we want to make a application in energy, like a solar energy light related. So we need to work on optical frequency. And these metamaterials, even at the microwave, typically ride on the metal. And the same thing for the optical frequency, usually metal will be involved. So we need to look at the metal property at optical frequency. And optical frequency metal behave different from the microwave property of metal. And the reflection index actually will be with compact with the negative real part. For example, we look at the aluminum, this equal to, from the table you can check the visible light, the red 650 nanometers, the reflection index is given by this one, and then you look at the permittivity, electropermittivity, and this is equal to, the mu equal to 1, so you take the square, and this one, you take a look at the square, and it gives you the negative real part. So the negative, the real part of electropermittivity already negative for the metal, the optical frequency. And you can understand why you have this one, and also it's a frequency dependent, and you can using the simple Joule model, starting these electron in the metal is kind of free electron. So you can look at the starting from Newton's law F equal to ma, acceleration, and then you look at the force in the electromagnetic external field, which is E, and then this is you look at this is a friction damping factor, and then the ma, and then you look at this one, and you look at the Max equation, substitute this one. Max equation, and you here, in order to get the electropermittivity, you try to replace the Jp with the current with the E field, and from these two equations, you can try to write the J, remove the H, write the J in terms of E, and adding on to this one, you get the electropermittivity, and electropermittivity, then you're giving this kind of form. This is called the Joule model, and from this model, you can see that you plot the gold cake, and then for this longer wavelength, and you see for low frequency, you see this will become negative. The real part becomes negative value for the electropermittivity. So this is a Joule model, and physically, it's because these free electrons in metal, they were, when you have the electromagnetic field surrounded, they will keep oscillating, follow the electric field like a free electron. And then you have oscillating electric field, so these electrons will also have this kind of distribution periodically. And it could be along the surface, the waveguide, and that is called the surface plasma. Polariton SPP, or you can have just metal spheres, array of them, putting them together, and they can still oscillate in this way and cause the resonance phenomenon. And now you move to the metamaterial at a high frequency, at optical frequency, and people start with like near infrared, and then you can make again still using the split ring resonator. And you can see that for this split ring resonator, if I apply the external edge field electromagnetic in this direction, edge field in this direction, and cause the this kind of current flow along this split ring, and then you can have this magnetic permeability become negative. This red curve becomes negative in this region. And in the other region, for this low frequency, actually, because it's oscillation resonant phenomena, this could be very large. It's larger, much larger than 1. And conventional material, mu, it's usually equal to 1 at high frequency. And now you can make it at high frequency, it can be very large. So it's not just because, and here could be very small, 0, negative, all these fields can make that one. And when you want to go to visible light, or even shorter wavelengths, and then Purdue University, Chalet, they proposed like large pairs of gold, and putting them together through displaced current, you can still make a kind of loop resonance, and then you can still have the negative reflection index at the near infrared region. And recently we proposed that go to shorter wavelength, even down to the UV wavelength. And then in this region, you could not using the split ring resonator because it's not scalable. There's inertial kinetic property that you cannot scale when you go to a very small size for these metals. So what we proposed is like a ring with holes and kind of ring structure array of them, and they close each other, and there's a coupling between them, and you stack of them together, and with this kind of structure, we can make double negative. So you can 4-layer, 5-layer, they already convert. Even single layer, and the losses can be very small. Field memory is very large compared to conventional one. Typically only like 2 or 3, but we can make the field memory larger than 10. Field memory define a real part over imagined part. So larger field memory means a lower loss. And then we can make this double negative in C certainly visible, like 550. And this is really your light shining here. It's go the negative direction, give you a negative reflection. And we even want to go further to the UV, like for solar cell application. You need to also look at the UV near infrared, not just near infrared, but also visible and UV. All these things take care. So for the visible case, and those shorter wavelengths, and this inner radius, it becomes very small, and less than 20 nanometer, and then it's difficult to fabricate. So we just simply fill the hole, make a disc, and these disc array of them putting together still give you a very good figure of merit for the metal material. And if we want to go to UV, deep UV, and then this distance between these different layers, these they become very small, less than like 20 nanometer, then it's difficult to control. So we just make this field this dz equal to 0, and then become nano y continuously. And these nano y's again at the UV give you a very good double negative metal material with a very high field of memory. So these are our structure different, and this can go to visible and to the UV with good figure of memory, very large figure of memory. And the reason why our design is much better than the conventional one, split ring resonator or pair of gold nano lots, because we have this kind of coupling here between them. And this coupling, if you look at the circuit theory, this coupling helps you a lot with additional term. And this additional term, S2I2, will shift the resonance to the short wavelength, high frequency. It helps you a lot with the same structure size or shifted to the short wavelengths. And that's why we can go to even down to the UV region for this meta structure. So now let's just talk about some abnormal property application of these metamaterial. And one example I want to show is zero index material, and for some energy related application. And first of all, we look at the permittivity nearly zero, absolute electrical permittivity nearly zero. What happened? What kind of thing, abnormal phenomena we can obtain? So we look at the first analytical solution with easier for this shell structure, and now this one is a permittivity equal to zero, nearly zero, and this is our vacuum, and we can easily derive the analytical formula for the radiant component of the electric field along inside. Inside is this metamaterial, and then you can see this term analytically can be very large, approaching to zero when D infinity when D approaches zero. So this will limited go to extremely large. And for the plane wave case, when the thickness of shell becomes very small. And this also valid if for a bar kind of nano large case, when this thickness of large becomes very small, and then in this case we don't have analytical formula, so we have relied on simulation, micro simulation. When the thickness of D becomes very small, and you see the electric field becomes singular, approach infinity, nearly when this D approaches zero, and while this magnetic field is still kind of constant, non-singular. And this is different from conventional surface plasma. Surface plasma electric field large only on the surface, but not internally. But here we can harvest the light, and this is going back like a plane wave shining here. All the field will be harvested to this needle, and all the energy will be just trapped inside this needle internally. And this just, if the needle, you pull the needle, becomes thinner and thinner, and the field, electric field inside just getting larger, even go to infinitely large. So that's different from plasma. And plasma, you can never have the field go to infinity. It's always finite. It's never go to like a infinitely large. This is different and also internal. So you can utilize this kind of harvesting, very efficiently harvest the light inside this bar. And another thing is enhancing the radiation. If we have permeability near zero, this structure, and I make a hole, I put in the light source inside, like an LED. And what happens if I design this radiance, this hole, that radiance appropriately, you see the radiation of the LED can be enhanced greatly by even like 100 times, depending on the design. So in this case, and you can think about putting LED here, putting the mu nearly to equal zero material, reflected it up, and then for the LED, just one direction radiation, I put in the metal here, block the downwards radiation, and then there's all the electromagnetic from the internal source will just go straight there and magnify and enhance radiation. Radiation, the power come out will be 100 times enhanced as compared to the LED without this metamaterial vacuum, just in vacuum. So this way you can enhance the brightness of the LED for the lighting. And in this case, we have already considered the loss of the material, metamaterial, and the imaginary part of the magnetic permittivity is not exactly zero, it's just very small. It's already give you a very good property for LED. And the third property I want to mention is the squeezing magnetic field. Magnetic field typically cannot be very large. It's like using the MRI, people talk about a few Tesla. And the maximal magnetic field you can achieve it's probably it's below like 100 Tesla, 50 Tesla, something you can maximally achieve. But electric field, you can make it as large as you wish, as long as you don't make this breakdown of electric charge. You can do it in the vacuum. Magnetic field is because quantum effect, also is the reason we cannot make it very large. But we can artificially squeeze the magnetic field to a very large. So now we look at the near to zero magnetic field, and then we carve the vacuum region like split ring shape, and putting the source, light source, whatever electromagnetic source inside, and we'll see what happens. All the electromagnetic wave will squeeze the magnetic field, squeeze to this gap region. And if you make this gap very small and approach to zero, you'll see the magnetic field approach to infinity, and it becomes infinitely large as you like. And while the electric field is just getting smaller, it's a very small value. And so this is the kind of strange. You can make a magnetic field very, very large, squeeze the magnetic field in this gap. And this is not a resonant phenomenon. You can make this gap in any shape, and the huge magnetic field region, it will just fill the whole region. So it's not related to the shape. It's just a gap region. It's not a detailed shape. So this shows the non-resonant phenomena is due to this material rather than the shape of the resonance. So these things. So then we want to use the absorbers for the solar cell. And the absorber for solar energy, there's two ways to, we try to using metamaterials for that purpose. The two ways to do that, one way is you absorb this solar light, and then all different spectrum you want to absorb. Absorb as much as possible for all the spectrum, and then this will become like a thermal source, and then you emit it. And then you need to redesign this emitter so that this emitter spectrum, emission spectrum will be very narrow, fitting your solar cell. Because solar cell typically cannot take good care of the UV and the near infrared, long wavelength, short wavelength, you cannot take good care of. Mainly, it's very efficient only at the visible region. But this thermal absorption emission from the black body radiation, they were pretty broad. So, and then you have a lot of energy still, again, wasted at the UV and the near infrared, and this solar cell couldn't absorb. But you can artificially design through metamaterial for the emitter, so that all the thermal energy collected from solar light will be re-emitted in a very narrow, efficiently concentrated, a very narrow spectrum, fit well for the highest efficiency of the solar cell spectrum. And then you will be, the whole system, make the photovoltaic system will be very efficient. So that's one way to utilize the absorber. Another way to use that, you just absorb the sunlight here, create a high temperature. And then here, you keep this low temperature area, create the temperature different, and then utilize thermal electricity kind of phenomenon, just convert it to the electricity that way. So these are the two ways you can utilize the absorber for the solar energy. So now look at the conventional material. In order to absorb light perfectly or very largely, if you typically people utilize anti-reflection or these kind of interference phenomenon, and then it relies on quarter wavelength thickness of this structure, because only through the quarter wavelength structure you can do the interference. One wave being reflected at the back side, another from the front side, and they were either in phase or out of phase. And then a minimal thickness is the quarter wavelength, so you can, through the phase control, maximize the absorption or minimize the reflection, all these things. So you have plate. So all these stuffs relied on, particularly in the military for the airplane coating, and it's extremely difficult to do it at the long wavelength, because long wavelength, that means you need a thicker coating, and because quarter wavelength constraint. But for solar cell application, same thing, you need a quarter wavelength. Now the question is whether you can make a coating for absorber as thin as you like, much smaller, much thinner, much thinner than quarter wavelength. And only by metamaterial you can achieve that. So I just give you one example, zero permittivity, zero index material. I coated the zero index material here and see what happens. So then you have the light comes down, and this could be very thin, the thickness of D1 could be objectively small. And then you have the first reflection, and then the second reflection might be scattering. And we do the simulation, and for this zero index coating, the wave come down will be completely absorbed. Even the thickness is much smaller than the wavelength, much smaller than the quarter wavelength, and all the waves come down, they will all absorb it by this one. And what is the physical reason why it's conventional material cannot achieve that, why zero index material, metamaterial can do that? And the reason is if the zero index material, first you get the first reflection, and then the second reflection, and third reflection. And for conventional material, they must be, in order to them to have in phase, the same phase, you must have at least a quarter wavelength, or quarter wavelength. If there's usually high phase shift, then quarter wavelength. If no phase shift, then you need a half wavelength, thickness. So they will be in phase, and then cancel this one, and there's no reflection. If the material has lost, all the energy will be lost because transmission is zero when you have a metal blocking. Now, with zero index material, then it's different, because all these material reflect the wave, because the index zero, they actually in phase. They all intrinsically they are in phase, because these phase is zero, because index is zero. So they all, no matter how thin it is, they all have the same phase. Phase is exact zero. So they always add together. They always add together, cancel the hard reflection, first hard reflection, and then make zero reflection, and then all the energy will be absorbed in this very thin layer. So with this one, you can do that. So we designed even experimentally here with our earlier simulation. So now it's only 1/90 wavelength thickness, and we can absorb the whole electromagnetic wavelength. 90% will be absorbed. It's very thin, and different absorption angles, 0 to 60, absorbed pretty well. And this is also consistent with our simulation. With these different angles coming, they will be all absorbed. No reflection at all when you're backed with the metal, with this material. And finally, I want to just look at the slow wave metamaterial. As I mentioned, the left-hand material have the backward wave phenomenon. The K vector is in the opposite direction of the pointing vector. So the wave actually works backward wave, energy gave forward, and utilize this kind of property. We can slow down light and use that for the slow light broadband absorber. So here it's a core, and we can put in metamaterial as a substrate, and the light in this wave guide it goes forward and then backward, because the backward wave, the metamaterial gives you backward. So you move like 4 steps forward, 3 steps backward, the next result only 1 step forward. So you slow down the light. With this kind of wave structure, 3-layer structure, you can slow down the light efficiently. And even you can trap the light 0. With this critical thickness, you can trap the light. The speed of the light will be 0. Will be stop, trap there. So then you can make this kind of critical signal light can be trapped depending on the critical signal, and you can slow down light. And you can use the dielectric material without the metal material, these metal dielectric with like photonic crystal of negative index, and you can do the same thing. You can slow down the light and even trap the light. And the light with this kind of taper structure, you can slow down. Now, so we can utilize this kind of slow wave phenomena. It's perfect. So now we look at this structure as a taper. The light comes down, and with this kind of structure, and there's a light will gradually slow down to 0 even. And for different component, frequency component, and they will be trapped at different depths. So here, this is at the first we test the microwave. So microwave, this kind of pyramidal structure, the electromagnetic wave come down, and then the different frequency component will be trapped at different depths and absorbed because the metal has some loss. And the material has some loss. They were trapped there at different frequency, like 8.3 trapped here, 10G trapped here, and the frequency increases. They trapped at the higher depths, and then they were completely absorbed in the material because they kind of squeeze all the intensity is very high and very effectively absorbed here. So it's a very broad, and with this kind of slow light, you can make it a very broad. And in microwave from 8 reflection is nearly 0 from 8 GHz to 14 GHz. It's like 50 over 50. As 6 over here, it's over like 60%. Respect to the central wavelength will be absorbed completely. So it's very broad absorbance. And then we tested for this. This is the microwave experimental result. Absorption is odd angle, frequency 8 to 15, consistent with our simulation result, absorbed very well, absorption. And then we tested this at the optical frequency and through 0. And with this optical stack of metal and plasmonic and thin field, putting them together, pyramidal form, and there will be different frequency components will be trapped at a different depths, slow down. You see the pointing vector, they come here and turn along and trap it here. And another frequency will trap here, and then because material loss, they will high intensity of light at this 0 index, 0 velocity region, and will be absorbed very efficiently, and we can make it as the frequency at the near infrared efficiency very, very large. And that's this optical work with collaboration with Professor Fang's group at MIT. So that's with that I just finished my talk.
Questions? I assume we're going to have time for questions? Yes.
You have mentioned that you can play with the emitter layer of the solar cell so that you can absorb the light in the range, so that it can emit the light in the range that you want, right?
Yes.
So how do you do that?
That's later. First, they have 2 steps. That's a good question. First is you absorb the light, all the spectrum absorbed. But then, typically, without doing some kind of special emission design, they were emitted in the same spectrum and also blow. And then you cannot, like this case. And then your solar cells, typical solar cell only work well at the visible spectrum. So this emission will also give you UV and also near infrared, and they will be wasted. So this one, so there are 2 components need to be designed. First, we need the design absorber efficiently absorb all the sound spectrum. So that's like a metamaterial can do very well. You absorb all the spectrum. That's what we call my next talk is called broadband absorber design using these kind of technology. Broadband. I want to absorb the whole solar spectrum. Broadband absorb. And after that, you also, in my third talk, we have touched how to use design emitter with go to the narrowband emitter. And this is the thermal. When absorbed, the temperature increase heat, convert to heat, and this heat give to the emitter. But you need a metamaterial structure, even like you can break down this black body radiation formula. The emission central frequency wavelength does not need to follow the black body radiation. Okay, so they will radiate to some of the spectral frequency that you design, you wish. And we wanted this to be narrowband, just at the visible light. So that you put in a conventional solar cell, they will be all absorbing. So that's the idea. So you need the two design. One is absorber, broadband absorber, and another one is a narrowband emitter. You're putting them two together through the heat. You convert through the heat effect. You combine them together.
I mean, what lighting factor that you are playing with in the emitter that makes you emit in the right range that you are interested in?
That's right. That's another metamaterial can play a role, make a special emission spectrum for this emitter. I will touch that in my third lecture. Yeah.
So another question is about the absorber layer.
Yeah.
Why can't you just use it as an absorbing layer in the solar cell directly? Because you said it's a very wide band.
Yes.
So why don't you just use it in your absorber layer in the solar cell?
Yeah. The absorbing layer, you use the solar cell. They will typically, in this case, will convert it to heat, not electricity. So you need some way to convert to electricity. So that's why if you use the only absorber, they will be absorber different from light harvesting. You know, in some of the solar cell, we can use the metamaterial to directly harvest the light efficiently and convert it to electricity. That's what we call the light harvesting. But it's not working as absorber. But absorber, it means typically you absorb the light, convert it to heat. They will convert it to heat, temperature increase. Then you have to use from heat to electricity. There's another process. So that's why these two processes converted from heat to electricity. Yeah. Which one you want to pick up?
Go ahead.
I'd like to know the mechanism behind the enhancement of the radiation of LED radiation. There's one slide showing using the metamaterials.
Yeah.
You can enhance the radiation of the LEDs.
Yes, LED. Yeah, that's in this one. We can enhance LED efficiently. You ask the physical reason or?
Yeah, basically.
Yeah, this is actually we did the simulation and then we will do the experiment and we'll check the physical explanation. But this one, the work done is only for theoretical case and simulation case. Without this metamaterial, you put in an LED light source and you can easily calculate the energy radiation, right? Just simulation. And then you put in this meta structure, you do the simulation again, you with the same source, light source, exact same light source. You will find, and you doing the pointing vector integration over here, you find pointing vector integration here is much larger than the one that you obtained with this structure in the vacuum. You compare to the vacuum case. Okay? And this physically, it will have some effect to the quantum, internal quantum efficiency of this LED structure. Okay? But you can look at this paper in detail. Yeah. This is for the radiation enhancement. LED.
Last question.
So you said that this structure can work in visible and nanowire can work in UV. So this type of structure will work for IR.
Yes, depending on for solar cell, these applications you usually want to, sometimes you want to enhance the one specific spectrum like UV. Typically people want to improve the efficiency of the UV, and then you need only the UV metamaterial in some of the case. And for the UV case, if you look at the literature, there's no metamaterial work well at the UV.
But this structure will work for IR.
For the near infrared NIR, there's a lot of design. Yes, very good. Figure memory pretty large. You can find it in the literature. And however, in the visible, it's not so much result, particularly with high figure memory. And we propose this one. And we like a disk case, a way of disk close each other, give you visible metamaterial. And this kind of little line can give you UV spectrum metamaterial. And that's the best design, to my knowledge, for the UV and visible internal figure memory.
Okay, I think we better wrap things up. Thank you very much. Let's take 5 minutes.